Greetings, class. We're going to do Whitlock and Schluter Chapter13, Handling Violations of Assumptions. I intend to do this in two segments. The first one, we'll look at Shapiro Wilk, NormalQQ plots. Second one, we'll do this non-parametric testing. Okay, so the idea here is this. Up till this point, we've done one sample and two sample t-tests, and we've assumed that the data has been normal or approximately normally distributed. Now, we'll also have the same assumption with later tests such as ANOVA and linear regression. Problem is, data are not always normally distributed. So, how do we tell if the data meets the assumptions, and what do we do when the assumptions are violated? That's our task. Okay, first off, detecting deviations from normality. What we have in the notes here is 4 different graphs. This one here looks pretty normal, so yeah, that's, at least it's plausibly normal. This one, it's got the basic shape, but this is on a z-scale, and you can see that we're going up to 10. There's not much data out there on a normal distribution, so the tails are what we call fat. This one here is more of a rectangular distribution, doesn't look too normal, and this one is more exponential. It's extremely skewed right. So how do we really check this? Do you just use a histogram? The answer is no. Histograms can be deceiving, and so I'd like to illustrate that here using R to start. In the 318 biostat file, I've got some scripts, and I'm going to go ahead and just run these right off the top here. What I've got is a data coming from a normal distribution, 10 observations, and that looks fantastic. This one, not so much. In fact, these two guys have 20 observations, and you'll see they don't look really normal, but the reality is they are normal. You can see as they've been drawn. Let's try another one. Boom, this guy's terrible. This doesn't look so good. This one, okay, yeah, you might be able to see that. Maybe here. And you could run these scripts and just practice a little bit. This will give you a feel for data that really is normal. What does its histogram look like? Not always that great, okay? So we want something better. Very good. So back on the lecture notes here, what I have is a thing called a QQ plots. Okay, a QQ plot or normal QQ plot is the following, and I didn't list it out here, so I'm just going to do it kind of in the crack. What you get is you have 2 axes. Okay, our first axis is what we call the normal quantiles. And then your second axis is going to be from your data quantiles, whatever they are. It's called the sample quantiles here. So sample quantiles. Now, what are the quantiles again? Remember, it's just the word for percentile, except you take it off the percent scale and put it on a 0 to 1 scale. So for the normal curve, we have some standard ones that we have memorized. Remember our 34-14-2 rule? Excellent. So there's 34% of the data. Here's 14%. We have the mean, 1 standard deviation below, 2 standard deviations below, and then 2% is all the rest. So, as we saw in class, our second percentile is right here. Our 16th is right here, 50th, 84th, and so on. We know all the normal quantiles, so they're fixed for us. Now, when the data comes in, it's going to get stacked up against these normal quantiles. And so what we want to see, ideally, is that those points are paired off. If you had an exact normal curve, then boom, they'd be on the line. Okay, boom. In reality, what happens is you might be a little bit off, and so you'll get some points here. You might cut a little bit below the line. You might just have some data around the line. And when you're near that line, that means that your quantiles are near the normal quantiles. And this is a more effective way of seeing normality. So bottom line, we look for points near a line. Does it have to be 45 degrees? That's the ideal, but if you rescale your plot, then 45 degrees doesn't matter. So these 4 plots are graphs of the data from the histograms shown in the first section. So this one should look good. This one should have fat tails, so we hope it violates. And then these two better violate somehow. So when I go down here, we see, aha, look at the line for A. That looks great. Very much on the line there. You can see the scale, it's not a nice even scale here. The bottom x-axis is much wider than the y. Okay, now this guy is pretty linear right here, but it takes this jump and a jump. That is indicating the fatness of the tails. Okay, so we're seeing violation there, tail violation. It's not a bad violation from normality. Many points are on a nice line, but it is a violation in that way. This one, by contrast, came from the rectangular distribution. And you can see that the behavior actually looks the opposite of these fat tails. Okay, it's very thin, and so it's sloped upwards. As your quantiles for the normal were theoretically large, then these ones were much larger. Whereas here, they're large. These were much lower, rectangular. Okay, and lastly, that extreme skew right distribution, the right tail went extreme, so that had our up, like the fat guy here. Whereas down on the left side, it was very, very thick, which matched up with the rectangle over here. Okay, those are the different behaviors that you'll see in a normal QQ plot. And these are in my R scripts. So in the first one, we'll go ahead and just plot this guy. And what I've done is I've taken 100 observations from a normal, 100 from a normal, and there's the normal QQ plot, so you can get a feel for it. This one is the 4 that we originally did, so let's run that. There's those 4 plots. They are random, so they would look slightly different each time you run, but the trends are going to remain as they are. Okay, so you can access the 4 plots. Now, last item. Okay, we have a formal statistical test in addition to a graph. So I recommend doing both. The test is called the Shapiro Wilk test, and it's very simple to run. The null hypothesis of the Shapiro Wilk test, let's write it out. So Shapiro Wilk test, null hypothesis, looks a little different than what we sometimes write, is simply that the data are normal. And that's what I want you to know. That's the null hypothesis. That's the assumed, the status quo, the nothing happening hypothesis. Then the alternative, of course, then, is going to be the data are not normal. And we run the test. We don't need to know the details of how that test works. I will tell you that it uses something like the normal QQ plot, where it takes the normal quantiles and compares them with the sample. Okay, and it runs those together. We don't need to worry about the test statistic. What's of interest to us is the p-value. So in graph A, we saw visibly, yeah, that should match up. We get a p-value way greater than 0.05. So we do not reject the null hypothesis. Okay, data for B. Look at this p-value, 1 times 10 to the negative 10th power. That is a radical reject. So we're going to reject the null hypothesis. Data are normal. Third one, this is not as radical as the other, but it's still very, very low. So less than 0.05, we're going to reject. And lastly, that extreme skew right, cut to the next page here, p-value is very, very low. So we will also reject the null hypothesis. And that is what we want to do before running a conventional t-test, confirm that your data is normal or not.